Yeah, so I know my talk was originally titled Machine Code, and I was trying to decide a few different things to show, but I decided I wanted to show something fairly practical about how does Julia compile and how can you turn that into an application. And I was initially considering like statically compiling Julia, but then realized like I'm asked a lot, how do you statically compile Julia? But Julia is always statically compiled. I don't know what you would really mean by dynamically compiling. Compiling is a static process that gets an output. So what I want to talk about is kind of a big statement. I feel like Julia is a ahead-of-time compiled language, statically compiled. I'm not going to quite touch on staged functions because that requires a little more nuance. But obvious question is, OK, wait a second. It's not ahead of time. It has a JIT. It's right on the home page. There's my screenshot that proves that it's JIT compiled. So what gives? Well, Julia uses a JIT because it can do performance-guided optimizations. It can see exactly what you're running at runtime and figure out if there's a more efficient version of the code and get a very fast runtime that way. But the design of the language and the semantics of the language are such that it's not baked into the language that you need to do that. And the really key difference there is that functions are considered to be static. And relative to languages that do need a JIT, like JavaScript or Python, you can't introspect the frame or see who your caller was. And these other features that would force the language to be actually JIT compiled and doesn't have an ahead-of-time representation. So yeah, I keep forgetting. I have a slide where I say a lot of those statements, wrote them out. The one key thing here, 265, as mentioned in the previous talk, is kind of where we get it wrong. 265 is where we compiled something and then we didn't check and make sure that it was actually running what we intended. And so occasionally then you see it running the wrong code, and that's something hoping we can fix very soon, and definitely working on that. As I was saying, the key difference between why we can be an ahead-of-time compiled language is that all of the function declarations are visible at what we call top-level scope. And top-level scope is allowed to do a lot more. Top-level scope is what you get when you call a val or when you are including a file. It has function definitions. It has type declarations. It can call using. These are all things that inside a function you aren't allowed to do. It's either a syntax error or a runtime error. And the feeling is this is actually kind of a natural separation. So the design of the language was such that you don't need necessarily the features that Python gives you, where you can eval a new function or edit and look up the dictionary of the local environment and modify that. And when you give up those features, you can get an ahead-of-time compiler. So how does that all work together? Well, we can kind of look here. This is the help screen for the Julia REPL. And as we look through here, the normal invocation, you get a REPL. You give it a function, program file to run, and you get kind of a scripting interpreter. But then we look down here, and there's some other outputs that aren't usually present in a scripting language, where we start seeing Julia acting a little bit more like a traditional compiler, a little more static. After it's run the program, it outputs a file that gives you the result of running the program, and it's already pre-compiled. And so really what we end up seeing is it's both. Julia has, there's an issue open that suggests, well, maybe we should separate these two, so there's like a clear division between which program you run. But they could also be symlinks for each other. They could accept all of the same arguments. There's no limitation internally. It might just be a convenience explanation. So when you're trying to run it as a compiler, there's so many ideas out there and all of these different things, and how do they come together? And so this is one of the other things I want to talk about here is all of these boxes and all of these pieces of the code base, how do they all fit together? What parts are essential? What parts are the compiler? What parts are the runtime system? And You might be thinking help, right? One of the motivations for this was a recent question on, ended up being opened as an issue 16798. It didn't stay open very long, but the question was, is there a hackable mini version of Julia? And so the pretty quick answer is not really. Julia is not a toy language. When you're trying to make a simple hackable language, you don't include a powerful type system. You don't make functions multiple dispatch. You probably don't include an optimizing compiler, don't include inference. So all these pieces could be viewed as black boxes. And so it's possible, I believe, after having looked at a lot of everything in the Julia language, that you can go in and you can make a change and tweak one little piece and see how it affects the rest of the compiler. But it's not really possible to get a simplified model of Julia as a whole. One of the things I'll point you to, though, Jeff's JuliaCon talk 2015, he was talking about the type system. There's a file in the Julia repo that's written in Julia, so you can see what the type system does. And it's a lot shorter than looking at the equivalent C file, jailtypes.c, which implements roughly the same algorithms. The Julia types one apparently has more correct algorithms, but the C version and Julia version are attempting to implement the same answers. As I was saying, Julia is easily hackable, so let's see what we can do with it. The first thing we can do is say, well, what if we run Julia without the standard library? So we've compiled Julia, we've run make, and now I just create a file with nothing in it and try to open that, output a new file. I'm just going to call it minicore. Spits back this cryptic error message that it couldn't open a file boot.jl. And so there's not really any documentation on this, what this is, because you're not usually needing to look at this file. This file contains all of the really core definitions that Julia needs to do anything. If you ever open up this file, you'll see it has definitions for like what a string layout is and how to create expressions, and it gives, it's just a lot more convenient to edit in Julia than to describe those same things in C to bootstrap it. So it refuses to start without that. Since that file's in base, we can go ahead and run it in base, and we get this really, really tiny Julia, 33K file, and we can even run it. So the next thing we can do is we say, Julia, hey, start up with that mini core that we just created. We get a little REPL back here. We can print strings, and it's looking like kind of almost like the full thing, right? Well, maybe not quite. Plus isn't defined. Plus is not baked into the language. It's a normal function. It's just a symbol. And so 1 + 1, you'd think that'd be really trivial, but nope, can't be there. All of base is just not available. So, OK, here I put out, this is essentially what the make command does at the end to go from that very limited REPL to something that is useful. And so the first thing we do is we create an inference image that contains all of type inference. That's what's making the code faster. The compiler for Julia, the optimization opportunities that it has, are written in Julia, slightly separated from the base code right now, oops, so that you don't accidentally try to edit it and then unexpectedly your program is getting inferred wrong. But it's much easier to write in Julia, as all of you are probably here because you've found that out. And so we could implement all of that in Julia instead of in C and have it's hooked up so that the compiler understands when it needs to infer something, it goes and requests the module to infer it. Second step here, then, we output the system image that loads all of the code that we're familiar with. Output file is a sys.o. If you've ever used a C compiler, sys.o is the standard object format for native code. And so in fact, we can then just pass that to our compiler, output our shared library object. And finally, we can show that Julia can go ahead and load that shared library object. It's a now has the full REPL available. But, OK, so now I've gone from nothing to everything, but I haven't looked much at what happened in between. So I want to show a little bit more about what each of those is. One way to look at that is to go through all the translation stages that happened between here's a Julia file and here's the code that you get at the end point. I'm not going to look at this, though. Jeff's talked about this in the JuliaCon talk of 2014. It's on YouTube, and you can go through this in detail and see how all of the data flows through the compiler on each of those stages. What I do want to look at, though, is all of the other pieces. So once you've gone through all of those stages, you end up with code. And that code needs to be able to run, and it needs a bunch of primitives that understand how to run. The first thing that we need for running is our /Julia executable program. This does the option parsing, prints out help messages, and it loads the standard library. It is very tiny. It's not quite this tiny because I didn't put any of the getopt parsing on here, but this is all it does. And all of the real work happens in the standard library that's contained in libjulia and the sys.so file that we just built. Libjulia is all of the C code that we have that provides the definitions for how the Julia language works. So it contains a garbage collector. It contains all of the built-in functions that let us tell the compiler that when we mean plus, it means adding these two integers together using the arithmetic definition of plus. And we can describe that to the compiler using these intrinsic functions. It has an interpreter. So we can actually run Julia programs without a JIT at all by running through this interpreter. It's just not optimized. So it'd be very slow if we did that, and it instead just opts to compile basically everything. Contains all the built-in types. Built-in types are things like any or a method, int64, things that just to parse the expression of a Julia file, you need to be able to talk about some types in order to get the compiler running. Those will have to be defined. The type system, how do two types intersect? Is one the subtype of the other? The dispatch system is implemented there. The compiler is part of that, although, as I'll do in a couple slides, it is actually optional. It can be taken out. It contains a lot of our system abstraction layer. We need to run on platforms that are written in C. The C header files are not platform agnostic, and the only way you can see them is by compiling a C file. So that has to be there. And then finally, it has the system image serializer, so it knows how to reload all of the code that you defined and saved into the sys.so file, and can reload everything that you've typed in at the previous session. And then our sys.so, this is all of the Julia code. This is Julia code compiled to native code, as well as all of the metadata that goes with it, strings that you've given it. The code is kept around so you can query it and introspect code LLVM. Has core, inference, and base in there. And then I like to think that packages are actually part of this as well. Packages take an extra step to get into the library, but it's still part of the standard ecosystem of Julia. And we're really hoping to be able to move more of Julia out so that it's not coupled to the development of the base language. And then maybe find ways of making it so more packages are available at the default REPL, even though they are external to Julia, and so you get a more flexible upgrading path. And then Julia's standard library or installation also includes all the dependencies, LLVM, BLOS, libgit2. These are various C programs that people have written, and there's just no reason to rewrite them in Julia when people have already done great work making these and testing them. So what is in core, inference, and sysimage? You'll notice there's actually a lot of the files that are the same here. So we can go ahead and reload a lot of these files and 2 copies. And both of these are in the system image. And the only difference is core image is really short. And then the final thing in core image is we load inference. Whereas base, we go and load all of your user code. And why do I point this out? Because the next thing we want to do is figure out how to build system images with exactly the code that we want in there. And I haven't yet shown you how to add code to it. So one of the ways we can do, and we've had for a while, is at the end of the system image build, it looks for this user image file and includes that and kind of builds up an application. Not terribly flexible. We've had some issues. The build environment's a little bit different than the runtime environment, so trying to get code to work is a little bit harder. The one that everyone here has used is probably compile incremental. I realize you don't know it by that term, or at least hopefully haven't had to see that, because that's what the compiler uses when you say using my package. If it has a precompile statement, it knows how to go invoke the compiler. It doesn't need you to go put all the files together. It knows how to say, using my package calls base.require, which knows to say, well, if I don't have that, I need to read load the file. If you haven't declared it as precompilable, it'll just execute all the statements. If you have, though, it'll execute all the statements in a separate process, a sandboxed sort of environment, so that it can take that result, create a cache file, and then the next time you need it, it's already right there and instantly available. And so this is also kind of a static compilation, but at a user level. And then, yeah, the final step is that the package is available, and that can be then worked on. One of the things that I know needs to be worked on more, and actually, from the last talk, I just stole a project.generate here, because deployment is not really a well-formed story right now. There's build executable.jl and contrib build sysimage.jl that will kind of help you take your code and package it together. They'll sort of generate a main function for you. So these tools are kind of available, and I think a lot of them work, but the tooling is just not really there yet. And that's something we're definitely going to be working on in the near future to try to make that a lot more predictable and reliable and easy to use. Other deployment opportunities include you can output to C code. It's an indirect step, so Julia already knows how to emit object files directly. Emitting a C file and then compiling that to an object file just gives you this extra indirection layer that is a little harder to compile, but if needed, it does exist. And then, yeah, so making it really practical means trying to be able to take all of these existing incremental images. Probably, it should be possible to just take an existing runtime library, say, here's all my code, here's all the libraries I need, and just get a binary back. But that's not easy as it should be right now. So this is a slightly different topic, but one of the other things I'm always looking at is profiling. This is something Oscar put together recently, and I'm hoping something like this will be in base soon, so we can just immediately see like how much time is being spent doing actual work versus how much time is being spent in different parts of the compiler, and we can really start to optimize, figuring out text. If you haven't ever looked at a memory file before, so the sys.dylib here, I'm querying it with the size tool, and this tells me how many bytes is the system image and what is each of them being applied to. Text is, for historic reasons I don't remember, what they have called code. Not readable text. So I don't know how they came up with it. And currently, that system image has about 4 megabytes of code. If you ever run with -- precompiled equals no, the 10 seconds of startup is regenerating that code. So that's where we have a lot of caching that goes on now, a lot of pre-compilation, a lot of static code is already in there. And so definitely looking to try to make that bigger so that the more functions can start up really fast. There's a section in here, the const section, so there's about 26 megabytes of Julia metadata also in here. So how many minutes do I have left?
You have about
Oh, okay. So I have a few different demos, and I wasn't sure how many I would be able to get to. One of the recent demos that we got starting to work here is IBM provided us some funding to get it working on PowerPC. So I can SSH into the PowerPC server here. This is an IBM Cloud PowerPC server, and see all of Julia. I think I need to make that a little smaller. So I ran the test suite last night to see how much it was able to complete in Julia, and it is passing almost every test. I'm not exactly sure what's going wrong with the, oops, I don't know what that just jumped. I'm not sure what's wrong with the Cholesky test, because that was passing the last time I ran these. The numbers test is a known failure. We're actually trying to test whether GMP throws a divide by zero error or aborts the process, and GMP decides to abort the process on PowerPC. So that one's not really in our control. I think Yichao put a patch out trying to get that one to work. So I might just not have that updated yet. And LLVM complains that it doesn't have certain atomics on there. But we are at the point now where we are pretty much able to support a number of platforms. We have ARM, ARM64, x32, x86, x64, and now PowerPC. So we're slowly expanding our ability to run on many platforms. Future work, I'm hoping we can actually start running on some really more exotic platforms soon. WebAssembly, I think, is getting close to being possible. There's a little bit more work to try to figure out how all of that works and how all the rest of the tool chain works. And it has some other odd questions, like how do you run a BLOS, which is an assembly library, on JavaScript? And yeah, lots of future work to deal with. I'm trying to make better code, faster code, better startup times, better distributions, better embedding. Trying to make it maybe so you don't have to call Julia init. You can just link against the Julia program, just as if it was any other C program, and transparently embed that in an application. There's addressing 265 is a big one. And
what's the parenthetical right after it?
Which one? Oh, that's the something you were mentioning, is that maybe we want to disable the 265 involves tracking all of the dependency chain between methods. Possibly we could strip out all of that information if you are trying to build release code and just say, I promise I'm not going to replace anything, and therefore you should just delete all of that metadata code, save this code space,
But presumably you do that at the end.
Right, so it would be at the very end, you just say, basically to get this number a lot smaller. We've got about 26 megabytes of metadata in there right now. I think that can be a lot smaller, but if we're including stuff like all of this dependency tracking, well, then that number's going to go up. And if you're embedding it and promising that you don't plan on replacing anything, then you don't need that metadata. And so I can take questions, or I can do more demos, whatever. Saw a hand in the back first.
You didn't mention it, but at the end of the last slide, it said moving forward on intrinsics to built-in functions.
Yes.
What's built-in functions?
So currently we have two different ways of the runtime system exposing functions to Julia. We have intrinsics, which provide the definition for things like adds, and we have built-in functions that provide other intrinsics, such as get field of or which other ones are intrinsic? It's kind of an arbitrary divide, is essentially. But it's been a historic divide that intrinsics were unable to be run in the interpreter. And now we have actual runtime versions of every intrinsic, and so they can be run in the interpreter, and that's no longer a critical distinction.
Also, at least originally, the intrinsics basically referred to LVM instructions. So they were just one-to-one with LVM instructions, whereas the other kind of functions operated on the Julia level object model, which is not part of LVM. So that was kind of the reason for it.
Right. So that's probably a better description of why, whether something ended up in one or the other, but there's no, having a runtime version of this means we don't need a dependency on LLVM to describe the language anymore. We can have a model of the built-in function, and then we can have LLVM provide the implementation of that, and have those two separated. So another question here.
Yeah, you were talking about kind of some of the metadata that was, I think you said 26 megabytes or something like that the other time. I'm just curious, what, I think I noticed maybe the last time I ran a Julia, REPL, it was around 70 meg before I did anything. I think Python, by way of comparison, by the way, is like 20 or something like that. If you run, it might even be
Okay,
less.
if you just start the rep.
So yeah, where is that as a priority right now? Like trying to cut down on memory usage?
From my perspective, it's something that I'm trying to look into and see where that memory is going. Most people have pretty large memory available to their machines, so it hasn't usually been a huge concern, but there's embedded platforms that don't have that available memory, and as long as it's trying to take 26 megabytes, that kind of puts a limit on what kind of devices that can be run on. I remember, I think you had a second part to that question, right?
Just what approaches might you take?
The basic approaches are probably trying to just figure out where that memory is going and what it's used for. If we do a deployment, we can probably delete a lot of the extra metadata, so you will no longer be able to ask it about how a function came into existence. It'll just be there. You could potentially delete all of the documentation that's in there. I don't know how many megabytes in there. I think it's only a small fraction, but there is some extraneous work there. Some of the other contributors to that are BLOS, actually. So relative to Python, if you start Python plus NumPy and have installed a fast BLOS library, you'll probably see a very large static allocation. And we can't really control that, although it's also mostly virtual memory and doesn't get really allocated until you use it. Another big contributor is LLVM. I think I was seeing on their dev list recently, they've discovered their table gen is generating too much memory at startup time, and they have some plans to restructure code, and so that'll give us savings as well.
That's good. Thank you.
James, had you looked at my light branch in Julia? Have you taken a look at that?
A little bit.
Answer some of the questions. I was actually to cut it down and still have very usable. One, it still had a REPL and was about less than half the size of installation. And when you look at max RSS, it was about half the memory usage.
Okay.
And then by cutting out the REPL, it went from 110 to 85 meg. It's a big difference because there's a lot of tables, dictionaries that are built just to do the latex, the emojis. It just
Right.
And I did that, and I did a make install, so I had a separate Julia for scripts because I didn't need REPL.
Yeah, so one of the things I think I mentioned in future work is moving code out of base.
Yeah, well, that's what I did.
So the goal here is to put it together so that we can get code out of base but still instantly available when you need it. And
Yeah, I meant
that's
the first part of that.
yeah. So one of the goals is to try to make that so it's transparent that You don't have to think about which one am I launching right now. Am I launching the script Julia or the REPL Julia? Well, that's kind of a question the compiler should, or the runtime system should be able to answer for you. And so that's definitely one of the ways that memory usage will be addressed as well. I don't know who raised their hand first, so whoever wants to, yeah.
All right, so like on the question of whether Julia is statically compiled or not, so like right now, to get efficient specializations, things have to be provably type stable a priori. Is there any thought to having a system where if you empirically observe that a certain section of code happens to be type stable, you could then specialize on it, even though type victims couldn't prove it was stable a priori? Something like what JavaScript does.
That is certainly possible. So I mentioned that we have a JIT, and we use it because we can do performance-guided optimizations. There's nothing stopping us from doing the standard JIT tricks of on-stack replacement or de-optimizations, as you're referring to. And it's potentially useful that we may want to do that, but it's not the default model. Generally, it doesn't require that for the speed that we get now. It's just a trade-off then of whether all of that work and complexity, right now, the person who could implement it could also spend time on something else. And personally, I also think we can do a lot better job at generating very generic code. Right now, we kind of either generate very specialized code that's very fast, or we generate very generic code, but it's not particularly fast. And I think we can do a lot better job of bringing down that divide so that the statically compiled code, just with the information it has and a little bit of information from the parent, can eliminate a lot of these runtime checks and get the speed without actually needing to have any extra compilation or replacement work. Yes.
If I understand correctly, the main contribution to package slowness, and I guess I wouldn't use the word load times, because in my mind, loading is fast. It's really first usage which is slow. Is the fact that we don't currently cache machine code when things span modules, right? So if I have a type defined in a module and I access bases push bang function, then that code doesn't get stored as native code. Am I first of all correct?
Right.
Because it spans modules. So what are the numbers on how bad would it be if we moved to caching the native code across modules? How much would that be? The sizes of the package.ji files and things like that?
I think that's something nobody has explored yet to understand that. And yeah, it's a good point. That like we generate this code at startup, and then you close the program, and it forgets all of that work that it did. And it should be possible to cache that code. And I don't know whether the exact model is going to be trying to get everything at the precompile level, or maybe we can generate incremental files to our incremental files. So every time you cache an additional function, it could generate some metadata and be able to redo just that portion of it without reloading the whole thing. And if you look back at the profiling slide I stuck in here, LLVM optimizations are a pretty significant portion of that. So just being able to avoid that should really help with that startup time. And other things like inference, it's present but not huge. The current system already eliminates all of the parsing, lowering, and other generation time. And so the combination of all of those, I think, will really help.
We have time for one more question.
One more question, or I can do a little demo.
Oh, yeah, you can do demo, definitely.
No questions. So one of the other little demos I wanted to show, if I ended up having time, which apparently we do, Ben Julia. is to run the Julia REPL and give it a few extra flags here. So I have in here compiled the system image in the not terribly exciting named X. But this is a special system image. I can tell it to ignore the compiler completely. And I'm telling it to ignore the compiler completely, in fact, because this image doesn't have any code in it. If the compiler tried to run, it would hit an assertion that said, hey, wait a second, I don't have anything to compile. And what we see is it works. There's a REPL here that is compiled and is only complaining about generated functions and telling me that it had to compile those at runtime. And then I don't know how many people ended up seeing the talk on the Raspberry Pi yesterday and got to see the slight delay between hitting enter after version info and the slightly faster version when everything is precompiled. So this is kind of just a local branch that I don't have really ready, but some of the ideas I'm exploring here are trying to see how small the system image can be, where all that memory is going, and how we can really get Julia to be faster at starting up and get that trade-off between running really fast versus compiling really fast. The other downside I can show is that if we call, say, rand of the sum of rand of 1,000 numbers, it took a little while. And if I was to do the same thing with the compiler, it's a little bit faster. But this is kind of where I was saying I think we can do a better job of generating generic code. And the code I generated for that top sum function is actually as pessimistic as I could possibly make it. And so having a factor of about 1,000 between the SIMD version and the most generic dispatched version that I could possibly create is, I think, kind of cool.
Okay, let's thank the speaker.
So the sponsors of the conference are going to have a few words next door, so we greatly appreciate if people would go on there. They've been generous enough to